Howdy, everyone, and welcome to the Smart Grid Center webinar titled Auto Layout Techniques for Displaying Large-Scale Geographically Enabled Power System Data. I'm Jonathan Snodgrass, and I'm a postdoctoral researcher at Texas A&M University. I'm filling in for Andrea today, since her voice is not fully recovered yet. So first, I'd like to ask you, if you have questions, to please post them in the chat window at any time, and I will ask them to Dr. Birchfield during natural pausing points or at the end of the presentation. Or if you have an immediate question, feel free to raise your hand and I'll allow you to unmute yourself and you can ask your questions during the talk or after. So our presenter today is Dr. Adam Birchfield. He's an assistant professor in the Department of Electrical and Computer Engineering. Prior to this, he was a researcher at the Electric Power Research Institute, EPRI. He received the bachelor's degree from Auburn University in 2014. His master's in electrical and computer engineering from the University of Illinois at Urbana-Champaign in 2016, and his PhD in electrical engineering from Texas A&M University in 2018. Dr. Birchfield's research is in power systems modeling, large system transient dynamics, application of synthetic power grid data sets, and the resilience of power systems to high impact, low frequency events. I'd like to turn it over to Dr. Birchfield.
Thanks, Jonathan. Really an honor to be able to give this webinar today, and I thank all of you who are here in attendance. And we have a lot of exciting things going on in the Smart Grid Center at Texas A&M, and hope this can be at least one point where you're connected to all the work that we're doing here. And what I want to do today is just focus a little bit on visualization side of research that we're doing here when we're thinking about large-scale electric grids, thinking about how to plan and prepare for the future of large-scale power systems, large-scale energy delivery systems, how to plan for those, how to operate them. And a big part of that is connecting the data sets, the grids, and the simulations with the humans that are associated with them, whether that's mainly thinking of engineers that are planning and operating the grid, as well as operators, technicians, and also communicating information about the grid to the public or to stakeholders in other areas, non-subject matter experts. Visualization comes into play with all of these things because it's the way that we take data sets and try to connect them to a sense of understanding, a sense of having meaning behind the results. And so these techniques help us to get new insights into large data sets. And what I want to do today is just dive into the details of a couple of specific algorithms that we've been developing recently, talk about how they work and how they improve our visualization abilities. There was a really good webinar, I think over a year ago now, that Professor Overby gave about visualization, that gave some more background, sort of general visualization concepts. And so that might be something to go for further reference. And there's, of course, lots of papers and other references out there as well. We have a lot of support for our research in synthetic grids and in visualization, and so want to recognize that support and also for the collaboration and all of the working together that's involved in doing this research. And so I just want to stop and recognize that for a minute. The two topics that I want to talk about today are two different algorithms for visualization. The first is called automatic line routing for clear one line. So this has to do with building one line diagrams and routing the lines in a way that'll make them easier to see and understand how the network is laid out. And then the second would be this concept of mosaic diagrams, where we show geographically embedded data in a way that's non-overlapping and can kind of give you a geographic sense of some kind of discrete data. So I'm going to talk about those two methods today. Before I dive into all of that, I want to talk for just a minute about synthetic grids. Just about everything I do in this area connects to this concept of synthetic grids. Synthetic grids come from the idea that actual power system data can be difficult to access. It can be restricted due to national security considerations, data privacy, and for a lot of reasons, the data that would be helpful for a lot of kinds of research is kind of hard to get access to. And synthetic grids are basically test cases that are public and don't include any actual transmission system data. And so what these do is these enable research in this area by having large-scale realistic public test cases. This is an example of one, this 2,000 bus test case that you can see right here. This looks very much like a grid in Texas, and geographically it's located in Texas. You can see that there's generators where the real Texas generators are. You can see that there's load centers where the cities are and where you'd expect in Texas. But if you look at the transmission network itself, if you know anything about the actual ERCOT grid, you know that there aren't 500 and 230 kV lines in Texas. And you look at these lines and you can see that they aren't where the actual ones are. That's to underscore the fact that this is a synthetic test case. It's totally fictitious. And this is really opening up a lot of opportunities for research. And so that's connected to this visualization research as well, because it enables us to kind of demonstrate and show our large scale system techniques without having to give away any actual data. So most of the work, and I mean, there's work in this project that would be involved with real data as well as synthetic data, but we use synthetic data a lot because it enables us to show a lot more detail more easily from a data security point of view. I want to just talk a little bit about how we build these things. These are built from scratch using an algorithm. It's a whole research area in itself. We basically mimic the process of actual power system planning, where we place substations with using public data associated with generators and loads, cluster them into substations, and build the substations up with buses and transformers, assign voltage levels, and so forth. Then we move into the transmission planning process, which is the most involved sort of algorithm for building these synthetic grids, where we put a network of transmission lines and transformers onto the system using an iterative DC power flow, contingency analysis based sensitivity process, and match a bunch of metrics, including topological, geographic metrics, contingency overload sensitivity. I had a webinar last year that talked about some methods for that. Then we move into the reactive power planning stage, where we get an AC power flow solution on the grid and add in some voltage control devices in order to have some realistic voltage control settings. And from there, we can add a lot of different extensions. We have transient stability parameters on these grids. We do a lot of work in the geomagnetic disturbance area. Because these are geographically embedded, that opens up a lot of new opportunities for research in this area. And one of those big ones here is these single line diagrams and building good diagrams and visualizations. You can see that this picture, of course, is a visualization in itself. And we've built this one where we show the lines where they are, and the generators there as circles with a size indicating the megawatts of the generator, and the color giving the fuel type. And that will come back in just a minute. This is another synthetic grid. The main characteristics of these synthetic grids that are really relevant for this research are that they're very large, they're complex, realistic, and fully public. You can see we can zoom into this 20,000 bus case, and you can get very detailed into the representation, but of course still totally fictitious, not representing a real grid in any detailed sense. So that's kind of the background. That's the initial motivation for having better visualization, is that we have these synthetic test cases and we want to build diagrams and other visualizations that really show us what's going on inside these systems. But of course, the applications are numerous, and including, of course, understanding what's going on in a real electric grid, both from an engineering studies point of view and from a real-time operations point of view. And there's lots of ways that we can take large data sets here. This is 20,000 buses. So, when you're running a simulation, and maybe it's a transient stability simulation with, time points every, every quarter cycle or half cycle, it's a lot of data. And so the whole idea of visualization is saying, how can we make sense of that as we run through the simulation, try to get some insight and best characterize all of that over a longer period of time. The first thing I want to talk about today has to do with the line layout algorithm. The idea here is when we're building synthetic grids, or when we have a real grid as well, say, how can we make a useful one-line diagram for them? The real one-line diagrams are built and maintained with a lot of labor. That's a really important part of the engineering process, is having good diagrams of a system. When you have changes to a system, you have to update the diagrams. When you have new system, you have to make new diagrams. A lot of times you just get the power flow case and you didn't get the diagram that was associated with it, then it can be kind of hard to understand what's going on there. So there's a lot of benefit they can have from some automated techniques to lay out these lines for a one-line diagram. The focus in this, all the algorithms I'm talking about today, is power system data that's geographically embedded. So we've got the buses already clustered into substations. We know kind of what substation each bus is at and where it is geographically, latitude and longitude, that sort of thing. And then we want to place those on the diagram. And there's a method that's not presented here in detail that kind of precedes the line layout algorithm, which is saying, where do we put the substations on the diagram? And you say, well, we'll put them at their geographic location. That's definitely a good starting point. A lot of diagrams, they just put them at the geographic location without any modification at all. But it turns out if you just do that, some of them are so close together, and depending on how big you want to make the substations, they can be pretty close together to the point that they're overlapping and can kind of be too crowded and hard to see. So there's a couple of different approaches for placing substations on a diagram that are that allow it to still be geographically embedded, still be geographically relevant, but not too hard to understand, not too clustered. And so there's a force-directed approach that has been used with some success, but tends to distort the substations quite a bit. So that's one option. But then there's also this priority queue greedy approach that I implemented to build this one, where you basically just move them as little as possible that you need to keep them from overlapping too much. So that's what I kind of did here. You can see this is a synthetic test case. This is actually, I think, the same one that I showed on this previous slide right here. Moving back to the current slide, this is zoomed up on the San Francisco Bay Area. So you got a bunch of substations here, and I've shown them pretty close to their geographic location while I still spread them out some without making them, go off into the San Francisco Bay or out into the Pacific Ocean. So the next goal here is to connect these substations up by putting the transmission lines in here. We want to put these in a smart way where they're not just right on top of each other, or not, they're going in a way that makes sense. So the basic line routing problem is, okay, here would be the generic line routing. Okay, you got your substations, you put your lines in there, you put them in a straight line path, and they just go directly between the two substations. And that works kind of initially. That shows something. The challenge is some places these get a little bit crowded. It's kind of hard to see. It's hard to, sometimes just drawing a straight line is not the clearest way to show where the lines are going. So the objective here is to add a few waypoints, a few bends into these lines to draw them not exactly in a straight way, but to, this is the objective here, is to avoid overlapping lines with substations and with each other while minimizing the number of bends and the total length of the line. So there are solutions that avoid overlapping and avoid intersections, but they make so many bends that things kind of go around crazy, and that isn't really easy to understand either. So it's kind of finding a trade-off. So here would be an example of one right here where I've taken that previous one. This actually has the line flow arrows added in as well, but you can see that these lines have some bends added into them through an automatic algorithm that routes them around so that they're not overlapping lines, and you can see it a little bit more clearly where they're going. Notice that these large-scale EHV lines are not bending to wrap around every single little substation in between, and that's kind of a visualization decision made to try to keep these from being super windy. I want to just talk about kind of how that algorithm works. This is called the Delaunay line routing algorithm. And this is all based on the Delaunay triangulation. Delinear triangulation is a fast order n-log-n algorithm that takes a set of geographic points like this and builds a triangle. The Delinear triangulation is shown here with these black lines. So it creates these triangles that are nicely shaped. And what this algorithm does is it uses those triangles as line routing channels in order to route a transmission line from one substation to another. Of course, if the line is going between, let's say, this substation right here, and if it was just going to this neighboring substation right here, then you've got a pretty easy route. It's not really going to be overlapping any other substations on its way, but it's the ones that are going across several different substations that are going to potentially have some issues. And so the way that this Delaunay line routing algorithm works is that you use these Delaunay segments, these black lines here, as line routing channels. And so if I take this, if this green line is a transmission line, I run it between these two substations kind of far away. And I have these red points that are the intersection between that transmission line and each of these Delaunay line routing channels, as I'm calling them. Then those become the waypoints of this transmission line. And then you can say, okay, well, this line is getting a little close to this substation right here, and you can adjust these waypoints along these routing channels in order to create a little bit nicer spacing around these substations. So you might move these two out a little ways. And so the algorithm is not that complicated. It's basically you set up this routing channels with the Delaunay triangulation, and then you start by routing the line straight through the Delaunay triangulation, like I have shown here. And you connect them up with their routing channels, and then you kind of iterate through adjusting the waypoints to ensure good spacing. And there's some heuristics that are involved in this algorithm where you analyze to make sure that the waypoints are far enough from the substations and from each other. And so you keep the lines adequately spaced from one another and from the substations. And that's kind of the process of this Delaunay line routing algorithm. Here's a couple more examples of this. So you can see here, this is from our 200 bus synthetic case, Central Illinois. We have the substations with some labels and a lot more detail on them. And you can see that some of these lines, if you take this line here from St. Joseph to Urbana, that would be going straight through this other substation if it were just a straight line. But because of the Delaunay line routing, you kind of see the routing channel right here. It took these three lines that would all be really close to each other and overlapping in kind of a mess, and space them out in kind of a nice, easy to see way. And a similar thing, you can see this line right here ended up having this bend added right here so that it's not going straight across this existing substation, this White Heath substation here. So that's kind of the idea of this line routing algorithm. This is not claiming that this is going to give you a perfect one line diagram straight out of the box, but it's considered a starting point that gives you a good initial diagram that you can then go back if you want a really high quality diagram and hand adjust these a little bit. And so we do that sometimes, but it's really good. There's a lot of applications for this kind of thing, which would be mainly if you have a power flow case that doesn't have a diagram, whether that's because the diagram you have is out of date, or you just got one from another system, or you don't have those diagrams, or in our case for synthetic grids, and you want to just get a quick look at it, try to get a good diagram that'll really show what's going on in the system. Here's one for that San Francisco Bay case I was looking at a minute ago, where you could see that these red 345 kV lines and the black, I guess this is probably 138 kV lines, have been routed around so that you don't have as many overlaps between the substations and lines themselves. We got a paper on this that makes this a little bit more quantitative, and we look at metrics, visualization metrics of how many overlapping lines we have. We look at the number of intersections, we look at how long the lines are compared to straight line, and kind of quantify how the performance of these diagrams are from visualization point of view. So that's basically the line routing algorithm. I'll move on to the mosaic diagram next, but I want to pause. I think I saw a few notifications there, Jonathan.
Perfect. Yes. So we got 3 questions in the chat. So the first question is from Derek, and he asks, is there any recommended or open source commercial solver or sources that can provide this auto layout capabilities?
So right now it's we don't have that. We've got the diagrams themselves in the for the new cases, and we have the algorithm is published, so you can look it up in the paper. The code itself, I haven't gotten that out yet for use yet, but that's definitely a goal to have at some point.
Okay, so I guess that kind of answers Ian's question, which was, are any of these features built into Power World yet?
No, they're not. I mean, Power World has some ways to lay out as far as the substations and spacing them. They have a new thing for the force directed layout. So that part isn't there, but the line routing, you have the default way that it lays them out, which is mostly a straight line. Yeah.
Okay, and then one final question from Art. He was asking, I'll just read it. He says, maybe this will come up later in your presentation. I recall that typically a transmission line's actual length is about 30% longer than the straight line distance. Have you looked at or are looking at ways to represent this characteristic?
It's certainly true that a transmission line will generally be longer than its straight line distance. Of course, it's got to bend. The goal here is not necessarily to look at the actual routing of the line. I kind of make the analogy to like a subway diagram. If you're in a subway, you don't really care the actual routing of the train tracks. You care kind of which is connected to what. And so, the focus here is more on sort of how to show it in a nice way, sort of like a subway diagram. So it kind of depends on what you're interested in. And these lines will be longer than, but from a visualization point of view, we do look at how long is the line as we drew it compared to how long it would be as a straight line. And so we have some metrics for that. And I think most lines are not more than 20 to 30% longer than they would be in a straight line sense. That's a good chance to clarify the fact that I'm in no way trying to say that, okay, this line here has a bend here and a bend here. Does that mean that's the way it is in reality? No, it's just a diagram. And so the algorithm determined that putting these bends in would help to make this a little bit clearer to see where it's actually going, instead of, so it doesn't get too close to this other substation down here, basically.
Right, that makes sense. We have a couple other questions. Do you want to keep going, or do you have time for some more questions? Pardon?
Yeah, go ahead and ask them. Yeah.
Okay, perfect. So there's a couple questions. One is asking if the substations are at fixed locations, but only the lines are moved to reduce the gaps between the substations.
No. Building these diagrams involve 2 things: 1, moving the substations, and 2, routing the lines around them. There's 2 ways to fix an overlap, right? You can move the substation, or you can move the line, or, well, I guess 3, you can move both. The ideal theoretically would be, okay, you optimize both. You optimize both the location of the substation and you optimize the transmission line. The approach that we've taken for this algorithm is to move the substation first and sort of set those locations, and then to route the lines around them. And it's a heuristic, co-optimizing is a difficult thing. The substations are placed, not exactly at their geographic location. They're spaced out a little bit, because sometimes you have 2 substations that are very, very close geographically, and so to show them on a diagram where you can see them separately, you really need to space them out a little bit. So they're spaced out just so that the substations don't overlap one another, or they don't get too close to one another. And then the lines, kind of have to deal with it from there. we don't allow moving a substation, as part of the line routing algorithm, and it's possible that that could be, added to the capabilities later. So yeah.
Okay, and that kind of covered Amit's next question. So we have a question from Maria. Do you have a way to zoom in or out of the different for the different voltage levels?
Right. So I guess I should. That's a good opportunity to point out, I guess, some context here. You have diagrams that are used in different ways, and sort of the old-fashioned way would be to have something that you print out and you hang on a wall or something. A diagram, of course, those are still used. You print out and you have a paper diagram, and for those, there's not really any zooming. You sort of just try to make it look as nice as you can at one particular zoom level. But the focus here is much more on sort of computer navigated diagrams. So diagrams that are going to be involved in some sort of power system simulation software or visualization software. And so, we're designing the diagrams with that in mind, with the idea that you would be zooming in and having different layers. And so, like, you're looking at this one, you say, well, you can kind of see there's some detail in this substation here in the middle. Well, yeah, that's because it's designed where, okay, now you can see where the substation fits into the big picture, but then you want to zoom in and really see how that's connected to the neighbors and what's connected inside the substation. You have the ability to zoom in. And the idea is we could design a diagram, with the location and where things are laid out and how the lines are routed. And then, the file format that you export that in could be a number of different formats that then could be read by different software and implemented. And so these are all shown on Power World, where we wrote out a file format that Power World could read in and make a diagram. Then you could navigate it and see it on Power World. But I've also exported these things to just like a SVG file, or and there's always opportunity to implement it in different ways.
All right, no, thank you for that. One last final question. Can this model be used for distribution transformers as well, or only for big substations?
Well, distribution visualization is another problem as well. And there's probably some potential overlap here. The key qualifications for this algorithm being useful is the main qualification is that there's some sort of geographic tagging. I mean, this is based on already having some sort of geographic idea of where things are. So if you have that, then some of these techniques could probably be relevant. Distribution is different. Distribution, of course, it's not a bunch of substations that are connected to one another. It's one substation, or maybe two or three, that then have customers that are being served down the line from that. And that's a little bit of a different problem, but I think that there's some overlap between this work and that problem as well.
Yep, and those were, I guess there's, let's see, there's one question that just came in. Let me see if I can synthesize it really quickly. I'll just read it because it's a bit of a long question. What is the main logic behind routing of by trying this line routing algorithm? It seems like the algorithm does not reflect the reality of the power system in terms of the transmission line investment, while the other aspect of the synthetic power grids are based on the existing power grid parameters and topology, e.g. probability distribution of the line impedance. Therefore, it may provide some inconsistency in synthetic power grid analysis.
So the logic behind routing these out in this way is that we already have a power system model. So we already know what the parameters of the lines are. I'm not looking at this route of this line and saying, oh, it's longer, therefore I'm going to give it different parameters. We know what the lines are, and the length on the diagram is not necessarily associated with its parameters. It's showing, I mean, the key takeaway that you want to get from the diagram like this is sort of what is connected to what and roughly where they are. And so, visualization is always taking the underlying data and then showing it. And when you're showing it, you're trying to show some aspect of it or some characteristic of it. And in this case, the idea is to show what's connected to what, and to show it in a way that we can really see that well. So, hopefully that at least begins to answer some of those questions. So.
Very cool. I guess we're coming up on 2:30, so I'll probably go ahead and let you
Yeah, we'll go ahead
continue
and
on.
I'll go ahead and present the next part, and then hopefully we'll have some time at the end as well.
Sounds good. Thank you.
All right. So the next thing I want to talk about is this idea of mosaic diagram. And the idea with mosaic diagram is that we want to show certain kinds of power system data that's geographically embedded in a way that recognizes that the geographic embedding is important, but also this is the key thing right here, is that the geographic data is distributed in a way that's highly non-uniform. So what do I mean by that? Highly non-uniform. There's lots of clusters, right? If you look at the Texas power grid, there's a lot of stuff going on near the cities, and a lot less going on, out in the country. And so it's clustered. It's not geographically distributed very evenly, and that means that if we want to show data that's geographically based, there's a little bit of a challenge there for displaying that. And I'll show you an example here. But first of all, this idea of mosaic is basically that you have small colored tiles that you arrange in such a way that it gives an impression to the viewer, and that can be in an artistic sense, or it can be in a technical data visualization sense, which is obviously what we're talking about here. Here's an example here. This is showing this synthetic Texas case, and it's showing the generators as squares here. And so I drew a square for each generator. I made the size of it proportional to the megawatt capacity of the generator, and then the fuel type is the color. So the orange ones are natural gas, and the gray is coal, and pink is the nuclear, and you have all this green wind out here in the west, and a few hydro and solar as well. You can see obviously if there's generators nearby or at the same location, they overlap. And if you looked at this, you might have the wrong impression that we've got just about as much coal as we do natural gas in Texas. That's definitely not true. There's a lot more natural gas, but the way it looks here, you might think that. But that's mainly because you got a bunch of natural gas that's all sort of overlapped on top of itself. You might also think we have 2 nuclear units. We don't. We have 4. This is using 5% of the display space, so I can always make these bigger so you can really see it better. But the problem is if I make it bigger, it looks something like this right here. Okay, you can see that a little bit better, but now it's overlapped even more, and it's even harder to see. And looks like Houston has like a few generators down here in the southeast, but in reality, it's got a ton. They're just mostly all covered up. So the idea of this is to say, okay, we want to show some data geographically embedded that's just with these tiles, these mosaic tiles. But the challenge here is how do we lay these tiles out in a way that we can really see what's going on, and so they're not overlapping each other too much, but we still want them to be geographically embedded in some way. So that's kind of the idea here. So here's the problem statement. We want to find an optimal location within a regular rectangular screen for a number of rectangular objects of different sizes. They could represent all kinds of stuff. So we have mosaic diagrams that we use for generators, like I just showed, but also could be buses, could be transmission lines, could be loads, or all kinds of things. And they could be a static or dynamic quality. We could have them kind of change over time, or it could be just like a one-time picture. It doesn't need to be a square, but really it's ideal if these things aren't like really, really thin and really narrow, or really, really thin and tall, or really wide and short. Ideally, they'd be kind of like a nice aspect ratio. And they also have a preferred location. So we really want them to be, and the preferred location is their geographic place. So we want them to be kind of near where they geographically are, but we want no overlapping. So that's kind of the problem of building these mosaic diagrams. And also computational speed is important. So mathematically, we can kind of represent this problem as an optimization problem, but this is not the kind of problem that's very easy to just throw into an optimization solver, and it's because we have these non-overlapping constraints. Makes it very non-convex, very ugly problem to try to solve, really challenging to try to actually get a full solution to it. So we're kind of stuck with doing some kind of heuristic approach. But the basic idea here is we want to, we have each X and Y of the different objects, and we want to minimize how close those are to this XI0 and YI0, which is their ideal location, their their target, their geographic actual spot, which is, before I was giving it to where xi equals xi0 and yi equals yi0. And that's good from a geographic point of view, but it's bad from a non-overlapping point of view. So when we add these constraints down here, as well as the aspect ratio constraints, this is just a boundary box constraints right here. We're basically saying we want to try to optimize in this way. So I want to talk about kind of the heuristic I have developed to do this. The problem is, as I was saying, is it's a disjoint feasible space. It's non-convex. We could relax the constraint, but really I want to focus on how can we really avoid overlaps in showing this, so we don't have something hidden that we don't understand. You could take a combinatorial integer approach, which would be the more standard way to solve this problem. But and so here's like one approach that you could use to that, but those end up being extremely slow and a lot of combinatorial possibilities. Really, we can't really even do anything that's n squared because of the size of these problems. Like something like branch and bound is really unworkable beyond about 7 or 8 tiles. So this the approach that I'm using is a greedy approach. We basically add each rectangle once to the locally optimal spot. And so when you're doing a greedy approach, the point of an algorithm like this, or the engineering design part of it, is saying, what order do I place them in, and how do I locally optimize the one that I'm adding in? And so there's a pure greedy approach where you're just putting them in, and then the method that I use is a little bit better than this, where we're taking this kind of to the next level, which is the horizontal packing algorithm. And so that's what I really want to talk about today, is this horizontal mosaic packing algorithm. I got a paper on this that it's a order n to the 1.5 in practice, and it gives much better results. The basic idea here is that we have these horizontal channels that we're packing the mosaic tiles into, that are continuous in the horizontal direction, and then we kind of start from the middle and pack the tiles in outward. And so we avoid any overlaps whatsoever. It is still some semi-greedy approach, but it packs from the left and the right. So let's see kind of what those look like. So this is what it would look like for a very small tile size. This uses 2% of the display space, shows the generators. This is the same diagram I had before. You can see that even though it's using very small amount of display space and showing things geographically, it has modified the location of the tiles so that you don't have any that are overlapping each other anymore, and you can really get a sense of what tiles are out there, and there aren't the hidden ones like there were before. And then as we make them bigger, you can see that it continues to ensure that these tiles are not overlapping one another. And you can also see that it has to distort things a little bit more now that they're getting bigger. This is with 10% of the display space. You get up to 30%, and it's really having to distort things, but you can still see that a lot of things are still quite close to their actual geographic locations. And then you can make them even bigger as well, up to this is the 50% of display space. I think I even have an 80% one as well. So you can make them as big as where you want to show the whole system in one thing, pretty much, or use pretty much the whole display space. You can't really make it any bigger without going outside the bounds. And you can still see with this that you can still see somewhat coal in the east, somewhat wind in the west, and it shows the different generators there, somewhat geographically, but not overlapping. And that's kind of the idea of this horizontal packing algorithm. There's different variations you could do on this. You could show areas. So here's showing the 8 areas in the system. You could show the voltage. So this is a way where we're displaying the voltage. You can see where there's high voltage areas and lower voltage areas in some places. I like this one here on the right. It's a little bit more advanced. You kind of have to study for a little bit, but this is showing the status of the generators. And so the green generators are the generators that are out of service, that are available to switch in, and then the red and yellow ones are the ones that are currently in service and operating, where the ratio of red to yellow is how close those generators are to their maximum. So the ones that are all red are operating at their maximum megawatt capacity, and the ones that are more yellow have a lot more room that they could be dispatched. So it kind of gives you a sense of where the dispatch is right now. And this is really helpful when you're kind of looking at the solution to an OPF problem and trying to say, okay, we solved this. What generators did it use, and which ones did it dispatch, and where do we have constraints, and where do we have extra space? And, so the visualizations have different purposes, but I just wanted to show a couple of other examples of how you could use these mosaic tile displays. There's different options for presentation as well. This one shows a minimum tile size so that you can make sure you can see them all. We have this one here that's got an emphasis on one particular area, or one particular area is a lot bigger than the others, and so you could see the things going on in the other areas, but you're focused in on one. Of course, you can make a dark background if you want to show it in a control room sort of thing. So I want to talk a little bit about how this works in more detail. I really like a lot of times to kind of show the results first, and then kind of show kind of how we got there. So now I want to kind of back up a little bit and talk about kind of how this works. If you look in detail, and I'm going to go back to the original one here. If you look at this one, for example, it may look like they're all just sort of packed in there, in any sort of way. But if you look at these, there's these clear horizontal lines you can see in there that are pretty much everywhere, and they're in powers of 2, and so you can see that they're split sort of horizontally in this way. And you can see that if you kind of push, if you think about sort of pushing a tile from the left or from the right, you can see that things would slide pretty naturally well. Notice that vertically it's not that way at all. There are no, you look vertically and the lines are not at all, and that's kind of by design. That's how this horizontal packing algorithm works. And as I said, we're putting the tiles in from the center outward. So we start with one here in the center, and then we're adding them to the left and to the right, and kind of pushing them as necessary. And so that's the basic way that this works. Let me go back to where I was showing the algorithm step in more detail. We split the whole display space into these discrete steps that are powers of 2, and we figure out how big a tile will be, give it a width. So the width can be a continuous variable, and that allows us to use any size we want for a tile. And then the height is some power of 2 that's appropriate for that. And then we can ensure that each tile has an aspect ratio between 1:2 and 2:1. And so then each tile is basically added in a 2-step process. We figure out where on the outside, the left or the right end, we're going to add it, and then we push that whole row in towards the center into a way that's sort of optimized. So from a data storage point of view, this is pretty fast to implement, because you can store this whole diagram as just a binary tree. And so if you want to search and find where a particular thing is, you can just search it in a log based time period. So so basically the process that this algorithm works is that you add a new tile. And so maybe you take this blue tile we want to add in. Here's the tiles we have already, and ideally it would want to be right here. That's the geographic location of it, but instead we have to put it basically right here, because we're putting it on the outside. But then we're also going to take this whole section right here, and it's going to end up being pushed a little bit, and it's going to be pushed in a way that's going to optimize that trade-off between geographic accuracy for each one of these tiles. So you pick the row based on sort of the optimal place. So maybe it ends up being placed right here. And then you have the pushing step. And the pushing step means that we pick a location you could push a lot, push a little, push none, and then there's a cost function that gets minimized with how much you push it. And so this pushing step is extremely fast because of the way the data is stored in the binary tree. The property of mosaic is that the tiles can be in any area in any preferred location. No tiles will be overlapping. The tile area will match the input exactly. The width to height ratio will be between 1:2 and 2:1. All of these are sort of generally accepted good visualization properties to have. Rectangles that are a good aspect ratio, things to be close to their geographic location, things not overlapping each other. You can force them within a boundary box if you want to do that. And most importantly, computationally, it's very fast to see. It's feasible in the original defined problem. It's suboptimal, but like I said, actually optimizing that original problem is very difficult. So, I think that kind of a good suboptimal solution is pretty good for this problem. So that's kind of the end of my discussion of these mosaic tiles. Basically, visualization techniques are important, and so coming up with new ones, coming up with new ideas, trying to get some new algorithms is, I think, a good thing for developing and kind of moving the industry forward. And in power system analysis, National Academy of Engineering recognized the importance of new visualization techniques. When it comes to visualization techniques, it kind of depends on what you're trying to show that'll determine what you really want to demonstrate or what technique you want to use. The two techniques I showed here, one is automatically creating one-line diagrams that has a lot of different applications for synthetic grids or getting a quick look at a case or having a starting point for a high-quality diagram. Then the mosaic diagrams are particularly connected to when you have some kind of discrete data that you want to show geographically. But anyway, I just wanted to kind of get some ideas out there, talk about how there's a lot of ongoing work in this area. Here's the papers that kind of talk about these different algorithms in more detail. And so I appreciate everybody's attention today. I'll take any more questions that we have.
Thank you so much, Dr. Birchfield. We have a couple of quick questions for you. One from Daniel. Have you tried something like an interactive mouse-controlled magnifying glass to selectively increase the size of the mosaic?
Yeah, so one of the things with these mosaics is, how would you want to, like I was showing the different sizes here, one option could be if we're implementing this in some way would be to say, do we want the ability to change the size dynamically? And you could certainly do that. That's not built into any software right now that I know of, but yeah, it definitely could be a possibility. Because there's different benefits. There's the benefit to this one where you can really see the geographic location of where things are, but things are pretty small. And so depending on what you're trying to show, this might be a good one here, somewhere here or here, that where you can really see, you got things a little bit bigger where you can really see them. So it kind of depends on what you're trying to do. So it really would potentially make sense to be able to switch back and forth between the different versions of it.
So here's another question. Once you have the grid modeled for a particular area, how do you prioritize the substation assets for particular threats causing substations to fail?
So maybe read that again.
Oh, sorry. It sounds like it's related more to how you created the synthetic test cases themselves. So this might be more of a question for a different webinar. But once you have the grid modeled for a particular area, how do you prioritize the substation assets for particular threats causing substations to fail?
Yeah, that's a good question. That's kind of part of building these synthetic grids. I'm gonna go back to this. I assume this references somewhat this slide here where I'm talking about creating the synthetic grids and sort of this transmission planning process where we're making a fictitious case from scratch, and we put the substations out there and we put the lines out there, and yeah, there's going to be some priority. If you lose a smaller substation kind of out in West Texas, it's probably less likely to have a big catastrophic impact on the grid than one of these more central ones on the backbone of high voltage network here in the load centers. And so part of the transmission planning analysis is coming up with metrics that do show like how the topology matters, and which of the nodes are more like they have a higher, there's a topological property known as betweenness centrality that shows kind of which nodes are more important. And then the other one, of course, is just doing simulations, doing electric simulations and contingency analysis and transit stability runs, and you can kind of see which substations tend to be more crucial to the integrity of the grid. And the grid is designed with robustness in mind, and so we hope that the grid, the synthetic grids, match the real grid in terms of the ability to withstand issues with one particular substation or even a couple. Hopefully that addresses that.
Yeah, I think that was a good response. There's another question, kind of, I'll rephrase it a little bit. It's more of how would you kind of compare your mosaic packing to something like a heat map in terms of the pros and the cons?
Yeah, so heat map, also known as a color contour, is another way to display data. That's, I should have put maybe one on here for comparison, because there are a lot of similarities between that and a mosaic display. So what a heat map or a color contour would be it'd be kind of like this, except for you would not have these different boxes or these different tiles. Like you would have a continuous color, map on here. Or it could be that you have sort of contour lines, like if you're going to be climbing a mountain, you would show the lines of where the elevation is, and it shows that over time. And a weather radar would be an example of a heat map or a color contour map. Those have advantage for any data that's continuous, for data that sort of varies in a continuous way over space. I mean, the power system, there basically is no data that varies continuously, geographically continuously, because everything is along lines and between substations. But there's some data that makes sense to show in a continuous way. So one example of that would be locational marginal prices. Usually LMPs would not be good for a discrete diagram like a horizontal packing mosaic. Bus voltages, I showed one with bus voltages here, but bus voltages is one you typically probably would show more in a contour or a heat map, but you could show it with a diagram like this. The advantage of a mosaic display is that you have these discrete objects. If you couldn't really show what I'm showing right here in a heat map or in a contour, because there's these individual discrete objects that you want to show. So it all depends on what you're showing, and I think there's some use for both.
Excellent. I'm not seeing any other questions. If anyone else has a question, feel free to type it into the chat or the Q&A box, or raise your hand if you want to ask it directly to Dr. Birchfield. I've gotten several comments saying great presentation and outstanding work.
Thanks. We will have these slides, and I don't know if we'll have a recording, but available on the website. And I think I put my email on the first slide, so feel free to reach out to me. In particular with these synthetic grids, we have a website where you can download this case with the diagram. You can download this, at least a case pretty similar to this one with the diagram. We have a bunch of cases on there with Power World diagrams that you can, and we also have the cases in other formats as well. So encourage you to be using those. Those are publicly available for anybody to use for the research, and they're publicly available, and we encourage you to use them, and you can use them for whatever you want. So feel free to contact me if you have any other questions. And thanks everybody for your attention today.
All right, awesome. Thank you so much, Dr. Birchfield.
Thanks, and thanks, Jonathan.
Alrighty. I was just responding to one of the questions. So it sounds like the recording and the slides themselves will be posted on the Smart Grid Center website shortly after the recording. So yeah, thank you again, Dr. Birchfield, for this cutting edge research presentation. So if you think of a question afterwards, Dr. Birchfield said he provided his email in the slides themselves, but we'd also welcome your attendance at the next upcoming webinar on February 16th of next month. The webinar will be held online on Zoom, and the presenter will be Dr. Miroslav Begovic, professor and department head of the Electrical and Computer Engineering Department here at Texas A&M. Until then, stay safe. Thanks for tuning in, and we will hopefully see you in February. Bye, everyone.
Yep. Hope to see everybody at the next one. Thanks.